So yeah, hi everyone and people coming in. So I'm not used to doing that usually, and I'm doing that on my free time. So it's something that I worked on a few years ago, actually. There are some bits and pieces on my blog, but that's perhaps the first time I'm actually presenting everything I did on optimizing actually my first plugin that I wrote. So everything is part of Audio Toolkit. It's a free open source library published under the BSD license. There are juice modules. It's available on Windows, Linux, Mac, also embedded platforms as well. It's based on a pipeline concept, so you can put filters one after the other, and the presentation is actually about one of them, optimizing just one of them. And the idea behind the pipeline concept is being able to reuse everything, abstract all the memory concepts, has lots of different stuff in it, and I won't dive into it. And it's supposed to be optimized for some SIMD stuff as well. Anyway, back to our actual presentation. So I will start with, I will present something on a really simple circuit. I don't want to be too complicated with really lots of math. There is going to be some math, but I hope you can bear with me. So it's just a simple diode clipper, and for people that went to Ivan's presentation before, you already saw that that circuit. So the idea is, how can we make the simulation of that circuit faster? So, well, here you have a derivative here coming in, and it's not straightforward to actually get a fast algorithm for that circuit. So back to it. So when you try to apply just your basic math on it, you end up with that equation here. So the issue is, as I've said, you have that derivative at the beginning, and you also have that hyperbolic sign, which means that you can't just say, okay, I'm solving the equation analytically. You need to discretize the equation and then use a fancier algorithm to actually get the result. So usually what people use is just a trapezoidal discretization of that derivative here, and you end up with that horrible equation. And that's just for a simple circuit. So when you have lots of different wave shapers, capacitors, everything together, well, it starts being quite hairy, and that costs a lot of time when you try to optimize that. So then, once you have that equation, you're not out of the woods yet, because, as I said, it's not an analytical equation. You can't solve just for actually the output here. I should have said that that first, yeah. The output, VO, is actually what we want to estimate. We have VI, which is the input, and we want to get our VON plus 1 actually after. So that's, yeah, it's actually badly written. There are some issues with the equation. Thanks, PowerPoint, for writing really great equations. So that's actually VON plus 1 divided by NVT. But yeah, thanks Microsoft. So when you try to get to retrieve that VON plus 1, well, you have it here, and you also have it here. So that's the issue. You can't just extract it out of that equation. So you need to solve. And to solve that, we usually use NewtonRaphson, or I haven't said that you can also use different approaches, but that's the first thing I actually did. And what you want to do is to solve that equation You put everything on the same side, and you say, okay, that's equals to 0, obviously. I mean, just you put a VON plus 1 minus VON on the, with H, and that's Fx equals 0. So what you want to the NewtonRaphson algorithm is just basically saying our new trial to get Fx equals 0, xn plus 1, is just a variation around xn minus fxn divided by its derivative. So on top of that big equation here, you also need to have the derivative of it. It's quite still simple to write for that kind of equation, but when you have matrices, it starts being a little bit more complicated, but you get the gist behind it. So the actual issue is, if that's something I'm going to show you, is to write a nice way, a fast way of computing fx and f prime x. So that's what I'm doing here. So you need to compute a bunch of exponentials. That's your hyperbolical sign. And in the derivative, you have the cosine. So that's why I'm just getting them out of here. And then I'm computing directly here the value fx, and I want to compute, and its derivative. And actually, the derivative is quite simple. It's just basically a function of the coefficients you have here, and also these fractions. So it's still quite simple. And then you get some timings out of it. So that's all done with Audio Toolkit, because there is an integrated profiling tool as well for instrumenting, just to tell me where I spend most of my time. So that's what it gave me. Gave me 1.2 seconds. Or that was what I got. Yeah. And then the issue is, well, actually, where do you spend your time? Because you have that. You have your NewtonRaphson algorithm there. You have these two things, and, well, how can you make that faster? You also know how many iterations you spent, and that's the number here. So that's 2.5 and something. That's the number of NewtonRaphson iteration on average I'm making for that. So also one of the nice things then is that you can do a profile. So I like doing that with Valgrind, and one of the plugin which is called Grind, and it's nice and it's not nice at the same time. Some of the people that know Valgrind know that it's quite slow, but of course it's emulation. And there are other tools that exist, like Vtune, and as Audio Toolkit is a free open source library, I also have a license to use it, but it lacks something that I really like about Valgrind and all its tools, and particularly Carcache Grind, is that nice heat map here. There are some caveats with it as well, because sometimes GCC just messes up everything, the order of everything, and you don't know something that you think is supposed to be at some place is actually at another place, and it's quite annoying. And there is also another issue with Valgrind, is that it doesn't store the full trace when it stores the result. It only saves the calling function. So that's why here, for my nice simple filter, I get that nasty embedded pieces inside something else. As I said, Audio Toolkit is based on a pipeline concept. So all the filters have the same virtual function that is called, which is process. So all my computations are actually below a process function that is called recursively. So that's what you have. That's recursive stuff. But actually, it doesn't mean that I always have my exponential in all my process. It's just an artifact of Valgrind. So that's also something I want to tell here is you have to know your tools and how they behave and their limitations. But still, I like that view because if you can have just one view and limit yourself to just one part, you can still understand what's going on. So obviously here, well, exponential, that's really bad. So one of the first steps is obviously to change these. I mean, there's no way to, I don't need to compute exactly the same exponential with just a minus here. Just for the sake of argument, let's go back here. That's just the inverse. That's for the hyperbolic sine and cosine. I need to have that minus here. And actually, that makes quite a difference, obviously. The algorithm hasn't changed at all. So I still have that same 2.5 iteration per sample. But the time is it's minus 30% and something. That's the first thing. But I still have lots of these exponential calls. So there are different ways to approach removing that exponential. Approximations, polynomials, and I have to say that I haven't been really happy with any of these. The only solution I found that is, well, first things first. You see, there are two calls here. Exponential for the past, so that's the current state of your equation, and that's the next step. But actually, that one is always the same. That one's, each time I'm doing an iteration, is actually exactly the same. It keeps on being, I keep computing that exponential for no reason. So one of the first trial I had was to, well, where is it? I guess I forgot, I didn't update that slide properly. Sorry, so that was, that one is supposed to be gone. Obviously, it's not on that presentation, on that slide, but that one, you can actually store it somewhere else and reuse it each time you go inside that loop. And if you do that, well, you have that small additional improvement. Still 2.5 iterations, so that's more or less the amount of exponential that you gain. You have 1.5 less exponentials to call per sample. And obviously, that blue area gets smaller. But actually, on Visual Studio, I couldn't see any difference between the version with the memoization and the version without. So I tried something different. That's how I can get back to what I said before, that exponential here. So instead of using STD, I'm using fmath. So that's something that is actually used in lots of domains, even at my work, actually. And it's another way of computing the exponential with some, what are they using? They are using ASAMD, it can be vectorized and all that stuff. It's quite neat. It's not perfect. It's a little bit less precise than std-exp, but up to the 4th decimal, so it's more or less on the ballpark for it. For what we are doing, it's the same. For double precision. For single precision, it's horrible. So I'm using it in double precision, and it works really, really well. Because without any exponential memoization, well, I get even another improvement in terms of factor. And now everything, all the exp is completely gone. Well, obviously that part is still quite big, and I still want to improve on that one. So going back at the beginning, we are trying to solve xn plus 1 equals xn minus f prime x divided by f divided by f prime. And we start usually with the sample that we had just before. So instead of starting always at 0, that's not something you want to start, you just say, okay, it's more or less on the ballpark of the last state, and I'm just going to evolve it a little bit, and that's going to be my next final point. So instead of starting with the x, well, the value of the last sample, I'm going to change actually the estimate of the original starting point. So that's what I'm doing here. So you still have that hyperbolic sine and cosine. And as I said, I'm not doing any memorization yet. So I still have to recompute these. So it's basically you just do you replace your exponent by an affine version of it. So you just say, yeah, around xn, well, x is 0 actually, I'm more or less linear. I mean, it's just to take the tangent and you solve for that equation. And that's the code for it. Actually, it's a little bit smaller than what we had before in the original equation. But the nice thing is that obviously you have one less iteration on NewtonRaphson, and it's still faster than the original one, just by modifying your original point. Everything is also faster here. And if everything is together, so you change exponential, you change with memorization and the affine estimate as well. And in that case, with that affine estimate, you can reuse the last point you computed for the memorization. So you don't have any exponentials here anymore. And in that case, get here. So that's an improvement of a factor of 3 with different ways of optimizing everything. And one thing I want to show again. So I'm going back here, actually. So what I did was to change that one with its usual electrical derivative equation. dV divided by dt equals c times the intensity. But there are different ways, actually, of writing that in math. So I'm going to replace that capacitor here by a resistor and a current generator. That gives me a simplified equation. I don't have any of that long. It's almost half the size that it was before. It's just an artifact of the font size. And actually, all the previous state, all the VON that we had before, all the VIN, everything else is actually just summed up in that equivalent current that we had. So solving for that, changing everything we used before, fmath, we gained a little bit again. But that's compared to what we had before. Actually, the number of iterations varies a little bit, but it's just you can't see it on the screen because it's a little bit different, but it's actually far faster. And I think I'm finished. What I wanted to, as I've said, to show is, as I've said, you need to know your tools to optimize something. I used Vtune. I used Valgrind. I also used Vtune, and it gives nice, shiny stuff, but it's also geared towards HPC. So sometimes you have all these red stuff. I mean, I'm single-threaded. I don't want to be over kind of saying that I'm using all the cores. I know that I'm using only one, so why is it red? It's just because they are selling all that stuff to other people, and they are not thinking about us. And they don't have that nice heat map, but they do have the full tree of all the calls. So I'm also using it from time to time. It depends on what you're doing. And then you need to really measure everything. Do profilings all the time. Do have a small command line tool that actually runs your algorithm and that you can profile, and then you can see what you're actually doing. Go to the GUIs if you like GUIs. Go to the command line if you like to have perf nice and tables. And then think, what can you optimize? Is it the proper algorithm? As I changed a few algorithms, as you saw. I changed the way I wrote the equation. I changed the original estimate. All that stuff can improve your final code. It may not, so that happens, and the number of times it was slower than what I did before. That happens. It's just a matter of measuring all the time to see that what you're actually doing matters. And I think I'm done. That's the repository for the library, and everything, all the code is also available on another repository because it's just another filter. And I think that's it from me.
Okay, does anyone have any questions, including online? I'll try and swipe them from my phone.
In your code examples, you had a -1 in one of the array indexes. I just wondered what that actually is doing.
Let me go back in time. Probably not that one.
So yeah, here the output.
Oh yeah.
Is -1.
Yeah, because it's Audio Toolkit, so I can do that. As I said, Audio Toolkit is based on a pipeline concept, so actually, and all the memory is handled by the framework itself. So a filter can say that it needs several samples before time 0 for the input and the output. So when you get to the next stage, the next chunk of data, you keep the samples you wanted in your original array. So this way, each time I'm going here, I always know that I have -1 because I said so in at the beginning when I configured the filter. And that's actually a call just for each sample of of the chunk. I'm calling that function with the current sample. So that's why I can go back in time.
Cool.
So that's the neat thing when you actually developing your own stuff.
Any more? It appears not. So let's everyone give a very warm thank you again.